All right, recording is rolling. It is Monday, February 13th. So let's do a quick quiz review, and then we'll do the AP classroom. Okay, so yeah, so you guys know we got a dynamics quiz tomorrow. Let's do open notes. We've been doing that so far. Of course, really, you guys should know how to navigate this right here because that's what you have on the actual AP exam. All right, so I was looking over the quiz I wrote for you guys over the weekend and say, okay, well, if you know these things, I think you're going to be all right. So free-body diagrams, you guys know you're going to draw a force vector, right? First, you put the center mass. Let's do an example of that for say like inclines, right? Can you guys draw? How about a block with no friction on an incline? Can you guys do no friction on an incline? Right, here's a block. Okay. If I said no friction, how would you draw that? Right. Are you guys thinking weight vector straight down? Okay. I usually MG, if you up sub G, force due to gravity, can do that too. Right. What other force do you need on this guy? Yeah, normal force, right? Which force is greater magnitude? Which one did I draw a little bit longer? The weight or the normal force?
The weight.
The weight, it is a little bit longer. Because in the back of your mind, you're thinking, well, the weight really, you want to split the components that are parallel perpendicular to the surface like that, right? This angle is that angle. If that's 29 degrees, that's 29 degrees, right? Okay. And then, this is, you guys could say this, right? You guys remember that, right? And that's what's equivalent to that, right? And that would be the entire thing for no friction, right? There's only two forces, right? You guys see two force vectors?
Good morning. My name is Lavanya Natarajan, and on behalf of NEHS, I'm featuring Malvin Gray Johnson for Black History Month. Johnson was an American painter who was born on January 26, 1896, in Greensboro, North Carolina. He was active during the Harlem Renaissance, and his work was much celebrated for his depiction of African Americans. As a child, he entered his work and won many competitions. Johnson later attended the National Academy of Design and continued to sell his artwork. The majority of the themes represented in this work portray Johnson's interest in spirituals and other aspects of the African American life in Harlem. Johnson died on October 24, 1934, due to heart failure at the age of 38. However, his paintings would come to be appreciated, and many of his works are now located in museums, private collections, and in historically Black universities. Thank you.
All right.
Have a good day, Hawks.
What if this block is at rest? Would you also include a force vector going this way, right? Going up to the right? And would it be exactly equal to mg sine theta, right? If it was at rest? What if it was sliding down at constant velocity? Wouldn't that look exactly the same, right? Except it would be kinetic friction instead of static friction, but otherwise it would look identical, right? What if the block is sliding up to the right? Which way do you draw the friction vector if there is friction? If it's sliding up to the right, there's friction. Which way is the friction vector? Down to the left, right? Okay, so there you go. There's a recap of that. Okay. So let's do okay. How about let's look at some Atwoods. There's two main categories of Atwoods you might run into. There's the classic Atwood. It looks something kind of like this. It might be like M sub A and M sub B, like that, right? And the other one you could run into, a lot of times they call it a modified Atwood, where there's a block up here, like a massless frictionless pulley usually, okay, and then another mass here, so it could be like MA and MB like this, right? Okay. If you want to, and we're going to see some of these in the AP classroom we do too, right? Here. Now, there is a few forces going on with each of these, but there's just a couple of external forces that really drive the system to move. Wouldn't that be the weight of this guy, mg, versus the weight of this guy, mg, right? And would the net force, the net external force be the difference between those two? Yes, okay. Yeah, but what about the internal tension force? Would that be less than the large weight, but smaller magnitude, greater magnitude than the small weight? Okay, so if I drew an internal tension, I'd want to make it like a medium force, F sub T. Would these be the same tension? Yeah, and this is a little bit smaller than this big weight. and a little bit larger than the small weight. So it can, the net force is down on the large one and up on the small one, right? Right, versus over here on the modified Atwood, there's only one net external force. That's if you assume no friction here. If there is friction, then that would also be an external force, right? But if there's no friction, then that's it. Now there is what does mass B provide then? Again, if there's no friction, maybe like inertia, right? To slow the system down, the larger MB is, right? The more inertia to slow it down. Okay. You guys think this tension here, F sub T, is equal to this tension here, S sub T, right? You guys think? And it might be, of course, MBG F normal. Okay, you see that? How about, okay, let's look at Newton's laws of motion. Okay, so law of inertia. If there is a net force on an object, what does it have to do? Accelerate, right? It could be speeding up, slowing down, or going around a curve also, right? You do constant speed around a curve, so it's centripetal force, right? Right. What if all the forces sum to zero, like zero net force? Like here, like I'm pushing to the right, to the left, it's zero net force. Okay? It might be at rest or it might be moving how? Constant velocity, right? Constant velocity, like straight line, same speed, right? So it's law of inertia, right? In deep space, if a rocket's going like 10,000 meters per second, how much force is required to keep the rocket going? Yeah, none, right? Because it's just going because of inertia, right? Second law, acceleration is net force divided by mass. I should have maybe throw a subscript net on that force, right? Because there could be like multiple forces on an object. You have to find the net force, right? Net force on mass, right? Atwoods are really good examples of that, right? And I usually take you guys through the macroscopic point of view, say, well, identify the external forces and then find the net force and then divide by the total mass, and I'll tell you exactly how much it's going to accelerate, right? The other way to do it, you guys saw this back on Friday, was you could set up a system of equations. You say, well, what's the forces on this guy? What's the force on this guy? You do a system of equations. It takes a lot more work, but it'll get you the same place, right? I think even for examples with conservation of energy and kinematic motion, you can get there too, right?
If there was friction.
If there was friction, okay, so this is probably going to drive this way, right? So friction would point which way?
So,
To the left, like this, a F sub FR. Okay, and which force would have to be bigger for this thing to be in motion, the tension or the friction force? Yeah, the tension would have to be overriding this, right? Okay. Or it's possible if they were the same, force, it might be at rest or it might be moving how? Yeah, constant velocity. If it is constant velocity, then those two would be the same, but also those two would be the same, right?
but the two tension forces would be different.
The internal tension is always going to be the same.
They're always. Gonna be
Yeah. Or the way AP will ask you, that'll always be the case. Now, in the real world, say, well, if this pulley has some mass and some friction itself, then the tension might change in the string. But AP never asks that. AP says that massless frictionless pulley and the internal tension, there's only one tension in the string. So, okay. There goes. Okay. Newton's third law. So we've got two kids on an ice pond, like pushing against each other, and they have different masses. And they push against each other. They push each other with the same force. Yeah, so equal opposite force. Anytime you have two different objects like pushing or pulling on each other, it's always the same force both ways, right? So equal and opposite forces. Are they going to accelerate the same? No, because they have different masses. That kicks back to Newton's second law of motion. Same force on both of them, different masses, different accelerations. Okay. How about elevators? Elevator question. So here's something we've done quite a bit. You guys know I care about elevators. AP asked you guys a bunch of questions about elevators. Suppose the elevator has a net force upward. Here's like the weight of the elevator. Here's the tension force, right? So it would be accelerating up, right? Could you guys set up an equation to determine the acceleration? Oh, it has some mass, right? Could you guys say net force is equal to mass times acceleration? The net force is the tension up minus the weight down, right? And then you can solve for stuff. If you want to solve for tension, you solve for tension. If you want to solve for acceleration, you solve for acceleration, right? Like here's what tension would look like. Mg plus Ma, or if you like, okay. Might want to memorize this one, M times G plus A. Okay. Now if they ask for an FRQ, right? You can't just jump straight to this, you gotta set this up and then go through each step, right? But if it's a multiple choice question, it's good to pull this out of your back pocket and solve it real fast, right? Right? Or if you had to solve for the acceleration of the elevator, you can do that too, you just do a different algebra. Okay. Yeah. Let's go with the elevators. That's if it's accelerating up. If it's accelerating down, then the weight would be more than the tension, so you can swap these two. Okay. What about what if the elevator is going constant velocity really fast? Right. Are these two force vectors the same? Yeah, they're the same. Doesn't matter if it's at rest or moving fast, moving slow. If it's constant velocity, these two always balance. Right? Zero net force. Okay. And finally, you guys remember you had that 10-part mini lab way back in the day, and one of them I had you guys do was you had like a spring scale and a weight and a spring scale and a weight and a spring scale and a weight. So it's like a chain, right? Say this is like 1 kilogram, 1 kilogram, 1 kilogram, something like that, right? What is the top spring scale rate? How many newtons of force?
30,
Yeah, pretty close to 30 newtons. How about this guy?
20.
20 newtons, and this guy 10 newtons. So that's straight off your lab from last semester. Okay. Ooh, now that maybe you're holding it at rest, maybe something like that. Okay. Hey, could I turn this whole thing horizontal? Like pull it across the pull it across the surface, horizontal surface. Right, it'd be a really similar idea, right? So if you're pulling this thing to the right, F sub pull, that pulling force might be 30 newtons. It's still going to register like 20 and 10 for it to accelerate, right? Okay. So you guys see if you're like pulling, because you guys saw a few questions like this last week, right? Where there was like a whole chain. Sometimes they had it pushing, okay? But so it looks like if you're pulling to the right, the greatest force is closest to where you're pulling. And then after that, so like this last spring scale is only responsible for accelerating a very small mass. So it only needs a small force, right? F equals ma kind of deal, right? They're all accelerating. Do they all have the same acceleration? They have to, they're all tied together. But there's different forces along the way, right? Goes down. Okay. What if you turn around and started pushing this to the left? Right? Now that pushing force, you'd have to push all three of them. So that'd be a huge pushing force here. I'm talking what this is now compression instead of tension. Same idea, right? Okay. But then as you go to the left, like this one, suppose it's in compression. Now it only needs a little bit of force to still push this little bit of mass. So the numbers could be the same, just in compression as you're pushing to the left, right? Okay. So it looks like wherever you're pulling, you're pushing, it's the greatest force there, and then it's less and less force as it moves less mass. Right? All right. If you follow that, should be pretty good shape for tomorrow. Okay. Okay. You guys got any other questions so far? All right, so let's move over to AP Classroom.